All right, let's go ahead and get into this last section of notes here for this unit. This is going to be 9.5, and today we're just taking a look at something that is similar to what we talked about in 9.4, just kind of the reverse, or what we call the inverse of it. So 9.5 is inverse trigonometry. Date that we're doing this is the 5th. An objective for today is we want to be able to use inverse trig functions to now solve for angle measures. So we talked a lot in 9.4 about being able to use these trig functions to solve for side lengths. Now we're just using it in a different way. So first off, a little review here. What are trig functions and how do we use them? Well, remember, I can use them if I have one side length and one angle in a triangle. I can use that to find everything else. So if I'm looking at this first example here, I see I have these two side lengths, x and 13, and we kind of talked about this a little bit, where you want to get in the habit of labeling them from the beginning so you can keep track of what trig function I'm going to use here. So I'm going to focus on 52. I see that I have x here, and that is opposite of my angle, or opposite of 52. And then 13 would be adjacent. Since it's not the hypotenuse, it's going to be adjacent here. Okay, so this is a good key to tell me what trig function do I want to use. Well, if I'm thinking of SOHCAHTOA, remember the one that has opposite and adjacent would be tangent. And so I'm always going to set it up, and I'm going to say tangent of my angle, in this case tangent of 52, equals opposite over adjacent, or in this case x over 13. Okay, and then one of the other things that we mentioned as well is before you start plugging things into your calculator, I would always try to get x by itself. So if I'm looking at this problem here, the way to do that, since we have a divided by 13 on the bottom, to get rid of that, I want to multiply by 13 on both sides. And remember, when I do that on the right side, they just cancel out, so I don't need to overthink that. I just get x. And on the left side, I have 13 times tangent of 52. Okay, and now that I have x by itself, now I would go ahead and just start plugging this into my calculator. So and you could do this in either order. I would maybe find the tangent of 52 first, and then multiply that by 13. And that should give you your answer there. And so I would say x equals, okay, roughly, if you did this correctly, it should come out to be about 16.6. Okay, in general, probably good just to get in the habit of rounding these decimals off to the 10th place, or in other words, the first decimal, because we'll be seeing a lot of that today as well. Okay, but that would be roughly 16.6. Okay, so like I said, that is how we set those problems up, and we do that with trig functions. The good news is for today, when we use inverse trig, our setups of our problems are still going to be the same. It's just going to be the process of solving for x, or getting that by itself, is going to look a little different. So first off, what does that mean for something to be an inverse function? Okay, well, inverse functions are just mathematical expressions. Okay, mathematical expressions that take the reciprocal of a value. Okay. The inverse, or in general, inverse functions are just mathematical expressions that take the reciprocal of a value. So, for example, here, let's just keep it simple, and let's just say we have a number. If I'm looking at a number, so let's say just like 10 or something like that, if I wanted the inverse of it, I'll just draw an arrow and say inverse here. I want the reciprocal, and we've seen this word before. It's been a while since we used it, but reciprocal is just a fancy math term for taking a fraction and flipping it upside down. Okay, so if I'm looking at 10, technically that's not a fraction right now, but I could write it as just 10 over 1. So the inverse of that would be 1 over 10. Okay, and this is an idea that you're going to see in later math classes as well, where it's asking you to take the inverse of something. And then notice, if I do it twice, if I take the inverse of it again, just like we talked about, it's just the reciprocal, so I'm flipping the fraction back, so that would be 10. So the inverse just kind of reverses something or flips it once, and then if you do the inverse twice, it brings it back to normal. Okay, so we're going to use that here with our trig functions that we have, because we're going to have to be able to get rid of them in these equations, and I'll obviously explain what that means in our problems. So for instance, inverse sine of here, what that really equals is I'll just write out this expression. How we write it is we say sine to the negative 1 of x. Okay, to the negative first power is the same thing as a reciprocal. And I'm going to say that's the same thing as 1 over sine of x. So we talked about in class on 9.4 that we just have sine of x, that's just a function. And now the inverse of that would just be what I get when I flip that fraction or take the reciprocal. So 1 over sine of x, okay? And then same idea works for the rest as well. If I want to write inverse cosine, I'd write cosine to the negative first of x, and that equals the same thing as 1 over cosine of x, okay? And then last one here, tangent has the same idea. Tangent to the negative first power x equals 1 over tangent of x, okay? And we'll see these come up today, and that's going to be very useful for us when we're trying to solve for these different angle measures here, okay? But just keep in mind, this is the three functions, the inverse functions that I want you to pay attention to. And your calculator should have all of these values in there: inverse sine, inverse cosine, inverse tangent. You might have to hit the second button to get them to pop up or to show up. And really, it's usually just the second button and then whatever trig function you're talking about. But we'll practice, like I said, we'll practice that here. So example 1, you can take a sec and sketch this triangle for me here. But it says I want to use inverse trig functions now to solve for the measure of angle A. So notice here in the past, or in the last problems, we're only given one of the side lengths. Now we're given 2, and we're going to use that because we can actually use that to solve for this angle here, angle A. Okay, so first thing, I'll just go ahead and label this x, just because it's the value that we're looking for here. And then if I want to go about solving this, I would actually do the same thing that we just did in those past functions, or in those past problems. I would label my sides first. So if x is our focal point, the angle that we're kind of zoning in on here, I would want to label my side lengths according to that. So 18 is opposite of it, and then 27 is the hypotenuse of this triangle. So we have opposite and hypotenuse. So which trig function goes with that? Again, if I'm thinking of SOHCAHTOA, that would be sine. So I'm going to say sine of x, because x is my angle here. Notice the setup is not changing at all. Sine of x equals opposite over hypotenuse. So in this case, 18 over 27. Okay, setup is not changing at all. The only thing that's changing is where the variable is. So now that we have this, notice we're not saying that x equals 18 over 27, otherwise we would just be done. We're saying sine of x equals that. But I want to know what x is. I want to know exactly what angle measure should go into that spot. So how do I get rid of that sine function that's all around it? That's where the inverse sine comes in. And you can write it multiple ways. I like to just write it with the -1. So for instance, multiply. I'm just going to take the sine of this one, and I'll put parentheses around here, sine to the negative first power of this as well. Okay, so it's kind of like you're multiplying it, I guess, but really it's just saying you're setting up this function. And the reason we do the inverse is because the inverse cancels out the original. So for instance here, the inverse sine and the sine cancel each other out, and we're left with x. Okay? So we have this here, we have x by itself now, and then on the other side I would write it this way. I would say sine to the negative first power of 18 over 27. Or in other words, inverse sine of 18 over 27. Now that I have this set up, now again, your calculator can do the rest of the work, because it's not even that I don't expect you guys to know what the inverse of sine or whatever this is. It's always going to come out to be it's usually going to come out to be a very odd decimal. And so there's no need for anybody to try to memorize these, because no one could really do that. So all I'm going to do is I'm going to go to my calculator, and first thing is I'm just going to do 18 divided by 27. So I'm going to get whatever that decimal is, okay? And that's going to be 2/3 if you want to simplify that fraction there. So 0.66 repeating. Okay, if I need to, I can write that. You don't have to. You could just keep that in your calculator, but I'll just write it here. 0.667 roughly is what it is. Okay, and then again, you just need to find the inverse sine button in your calculator. Most likely what it is, even if you're on an iPhone, is you want to hit the second button, and then you want to hit sine of that. Okay, and you can do this all at once as well if your calculator can hold this in. If you're on an iPhone, you need to type your decimal in first. If you're on a calculator, then you can just hit inverse sine from the very beginning, and then whatever your fraction is. Okay, but in any case, you set this up here, you type that in, and it should spit out a number here. And then as long as your calculator is in the right mode, the inverse sine of this is going to be 41.8 roughly. Okay, and again, we're getting in the habit of rounding that off to the first decimal place. Okay, and then since this is an angle measure as well, I'll go ahead and add on a degrees sign. So this is roughly 41.8 degrees. Okay, And then notice I could use that to find the other one as well. Okay, but this is the idea. This is what we're talking about today. We're using inverse functions to solve for our variables here. Okay. All right, practice this a couple more times here. Our example 2, we have this triangle here, and we want to use that to find measure of angle R. So just like the previous problem, I would probably just recommend labeling whatever angle you're looking for here. So for instance, I would just label that X. And now that we have this as our focal point, we can go ahead and label our side lengths as well. So notice 12 is opposite of it, and 8 is adjacent to it. And so if I were to go to set up this trig function, again, think of SOHCAHTOA. TOA is the opposite and adjacent, so this would be tangent. So I would say tangent of X equals opposite over adjacent, so 12 over 8. Okay, if I wanted to, I could simplify that fraction as well. It doesn't really matter. And then to get X by itself, before I start plugging things into my calculator, I need to get rid of that tangent function. And so our process of doing that is to do the inverse. So the tangent to the negative first power on both sides. Okay, when I do that on the left side, they cancel each other out, leaving me with X. And on the right side, I'm just going to write inverse tangent of 12 over 8. And like I said, if you have a calculator, you can just hit this from the very beginning. So you can just hit inverse tangent and then 12 over 8. If you're on a phone or something like that, you need to find that decimal first, which should just come out to be 1.5, and then inverse tangent of that. Okay, you're going to get X equals about roughly 56.3. Just get in the habit of rounding that off to the first decimal place. And again, I'll go ahead and put a degree sign there. Okay. Again, this is the idea. So the good news for these kinds of problems is the setup is the same. You're still looking at what sides you're given, and that helps you find your trig function. The only difference now is just solving for X in a different place. Okay, one more here, and then we'll have one final example that dives a little bit deeper, but making sure we get the basics down here. So in this case, it wants us to find the measure of angle X. And you'll notice here, whenever I'm asking you to find an angle measure, it's never going to be the 90, or it's never going to be the right angle, because we always know that's just going to be 90. You'll notice that's never going to be a focal point, whether you're dealing with trig functions or inverse trig. Okay, so measure of angle X here, I'll go ahead and mark that. Again, we look at the sides that we have, and I can go ahead and label those. I would say 15 is adjacent to this angle here. And then notice, we said this in class last time as well, 25 is technically adjacent to this, but it is the hypotenuse of your triangle. So that's always going to remain the hypotenuse, or that's always what I'll label it as. And now again, if I'm thinking of the trig function that I need to use, this is adjacent and hypotenuse. That would be the c part of SOHCAHTOA. So I'm going to say cosine of X equals adjacent over hypotenuse, so 15 over 25. If you want to reduce that down to 3/5, feel free to do so. Okay, or 0.6, whatever. Okay. So we have this here. Again, I want to get X by itself, so I'm going to take the inverse cosine to get rid of that cosine function. So these cancel. I get X equals inverse cosine of 15 over 25. And then just type this into your calculator and let your calculator do the rest. So here we have this. The decimal comes out to be 0.6, and then you just take the inverse cosine of that, and I'm going to get X equals roughly 53.1. And just like we've said on the last ones, this is an angle, so I'm just going to add a degree sign at the end here. Okay, always good at the end just to double check and see if that makes sense here. So 53.1, for example, looks like it would make sense, or could be roughly what it is. And notice one of the biggest things, or one of the biggest keys that'll help you out, is it should never be over 90, because we know these other two angles in this right triangle have to be acute. So that's one kind of key mistake that you can be looking for, or at least a little way to check your work. Okay. All right, last one here. Like I said, we're going to dive a little bit deeper. So it's saying now if we have a triangle, let's say I just have two side lengths, could I solve for everything else? Okay, could I solve for the remaining side lengths and the remaining angles? Okay, and obviously one of them we know is just going to be 90. Okay, so first, if I want to start with this, if I want to start with the remaining side lengths, we have a way that we can do this. So I'll go ahead and just label this a variable here. I'll go ahead and label it X, it's fine. And remember, we talked about this. If I have two of the side lengths and I need the third, and it's a right triangle, I can use the Pythagorean theorem. So this would be one of my legs, and this would be another. So I'd say 5 squared plus x squared equals 9 squared. And now I'll go ahead and simplify and solve this here. So right here, 5 squared is going to be 25 plus x squared equals 9 squared, which is 81. Continue to try to get x by itself. To do that, I would need to subtract 25 from both sides. When I do that here, these would cancel. And I'm going to be left with x squared equals, okay, good mental math practice for you, 81 minus 25. That's going to be 56. Okay, and then last step here, take the square root of it. And so I get x equals, okay, this is not going to come out to be a whole number, so I'll just leave it as square root of 56 right now. Because there's no whole number times itself that gives me 56. And then remember, we've talked about this as well. We've said if we can simplify this radical, then we want to do so. So this is kind of going all the way back to 9.1 and coming full circle and practicing everything that we've talked about in this unit. So square root of 56, I want to look at that and I want to try to determine if there's any perfect squares that are factors of 56. And there is one of them. Number 4 does go in there, and that does go in 14 times. So x equals square root of 4, square root of 14, and we know square root of 4 is just 2. So this is 2 root 14. And then last thing, just to double check, can I simplify this radical anymore? The square root of 14 does not have any perfect squares as a factor other than 1. So this would be my final answer here for x. X equals 2 square root of 14. Okay, and if we wanted to, we could get that as a decimal as well, but like we've talked about in this class, we're practicing just simplifying radicals. Okay, so I'll go ahead and label this here, 2 root 14. And really, I wouldn't recommend using that for any of your other problems or to solve for the other angles here, because if I don't have to use a decimal, I'm not going to. Okay, and then last thing here, other than the side lengths, it wants us to find the remaining angles in this triangle. So it doesn't matter which one we start with here. This can be done multiple ways. So let's just say we zone in on z. Let's say z is our focal point here. And to keep it simple, we'll just label this variable z as well. Okay, we could label it y, we could label it, any of the letters or anything like that, but we'll just label it z for simplicity. And if I'm focusing on z here, I actually have all 3 side lengths. And I could label these here. This would be opposite, adjacent, and hypotenuse. So theoretically, I could use any of my trig functions. I have the side lengths that I would need for sine. I have the side lengths that I would need for cosine. I have the ones that I would need for tangent as well. Okay, but like I was just mentioning earlier, if I have the numbers 5 and 9, I would just recommend using those because the other one has a decimal and I would rather avoid that if I can. If you're given a triangle with all 3 side lengths and all of them are whole numbers, then just take your pick. Doesn't really matter which one you choose here. Okay, but I'm going to use 5 and 9 here, so I'm going to use opposite and hypotenuse, which means that I need the sine function. So I'm going to say sine of my angle, in this case that's z, equals here, opposite over hypotenuse, so 5 over 9. And now we just go back into the same rhythm that we've been doing for these whole notes. I need to get the variable by itself, so to get rid of the sine function, I take the inverse of it. Inverse sine on the left side, inverse sine on the right side. When I do that, these cancel, leave me with z, and then I just need the inverse sine of 5 over 9. So you could just go ahead and type that into your calculator as is, okay? Or feel free to find the decimal first. But in any case, I should get z equals, and that's going to be about 33.7 when I round that off to the nearest decimal, okay? So 33.7, and that's degrees. So I'll go ahead and label that as well, 33.7 degrees. Okay, and then for the last one here, to solve for angle x, okay, we'll call this, we'll just call it measure of angle x, not to be confused with the variable that we had earlier. Okay, measure of angle x here. If we wanted to, we could set this up multiple ways. We could either use trig functions, because we do have side lengths that we can use to do that, or even easier is I know all 3 of the angles in this triangle are going to add up to 90. Okay, so I could say 90 plus, or I could say this is the same thing as 180 minus 90 plus 33.7. Okay, or a simpler way of saying it, measure of angle x, this is the same thing as 90 minus 33.7. Because you know those remaining 2 angles here would have to add up to 90. Either way you slice it, you're always going to get the same answer, no matter which method we just talked about that you use. But in any case, measure of angle x is just going to be 90 minus 33.7. So you could do this in your calculator or get some good mental math practice. But in any case, it should be roughly, and we're going to put the about sign here, which is going to be roughly 56.3. Okay, and we're doing that because we rounded off the other one as well, so it's not exactly 33.7, which means this last one isn't exactly 56.3, but it is close enough. That would be the decimal that you would get. Okay, so putting all this to use here, this is just good practice throughout our entire unit, using Pythagorean theorem, simplifying radicals. If you can do a problem like this, then you're pretty much ready for anything we'll throw at you on this unit review or unit test. Okay, homework for this is 9.5, and that should be posted on the class website. And as always, if you guys have any questions, feel free to let me know. All right, thanks guys.